For our next topic, we're going to talk about slope. And slope is actually something that we have looked at before. We looked at slope when we went out and calculated the ADA compliance of ramps around campus. So now we're going to look at slope in a more data-driven context. And so just here's a little picture of some examples of slope. So just to remind us, slope is a representation of the steepness of a line. So we've got the pyramids and someone skiing and the Leaning Tower of Pisa and actually a ramp up onto a truck. These all represent slopes. These all have a slope to the slant in the examples. So just as a reminder, again, we've looked at slope before. So slope is equal to rise over run. So slope always represents the rise over the run. And slope, we actually are going to introduce a variable for slope. So we don't have to always write out the word slope. We're going to use the letter M. That comes from the French word to climb, monter. So we're going to use M. And M is going to represent our slope. And our slope, again, rise over run. We're going to say this a lot. Rise over run. And rise over run is a vertical change or a change in the y. So that's vertical change over horizontal change. Okay, so lots of ways to sort of visualize slope, but we are going to use that variable m. So now let's come down here and take a look at if we had some actual points on a line, if we had some ordered pairs, because that's how we're going to be calculating the slope. So if we had some ordered pairs and we needed to calculate the slope, we have to find the rise and the run. So I just took two ordered pairs. I called this one x1, y1. So this would be 0.1 and this would be 0.2. So we'll just call x1, y1 0.1 and x2, y2 0.2. And if we were looking for the slope, we need to find the rise and the run. So I'm going to draw a triangle. Just like we did when we did ramps, I'm going to draw a triangle right onto this line. And the rise is this distance on the vertical line here, and the run is this horizontal distance on the triangle. So the rise is the difference between the two y values, and the run is the difference between the two x values. So that's how we're going to find, notice the rise comes from right here, and the run comes from right here. So our formula for the slope. So slope, again, we use the letter m, and our formula for the slope is rise over run. So we're going to take y2 and we're going to subtract y1. That's going to give us the rise. And to find the run, we're going to take x2 and subtract x1, and that's going to give us the run. Now this, let's give this a bubble. Let's give this some fireworks. Let's highlight it a little bit, because this formula we are going to utilize often throughout. Here, we'll give those fireworks some highlights here even, because this formula we are going to use often. And again, you don't have to memorize formulas in this class. You can always reference your notes. You can reference the formulas, but this is one that we are going to use so much that I think you will actually commit it to memory just through usage. So I'll highlight just the important portion. And just to remember, we always think slope is rise over run. It'll be a broken record. We'll say it often, but it's the difference in the y values, y2 minus y1, divided by the difference in the x values, x2 minus x1. Okay, so let's do our first example. So if we wanted to find the slope between 2 points, and so I just drew the 2 points here. We'll do it generically to begin with without context, and then we'll do an example with some context. So if we wanted to find the slope between the points 3, 7 and 8, 4. So those are our 2 points. I've graphed them over here. We can see on the graph right here that if we were to draw the triangle, we can actually draw the triangle in 2 ways. But if we were to draw the triangle, starting here, whoops, I went too far. If we were to draw the triangle starting here at this first point, that we would actually be going down. And that makes sense because the rise drops here. We're actually going down. This is a downward slope, right? If we were skiing across this page, this slope happens to be a downward slope. Okay? And a downward slope, by the way, will be a negative. Will give us a negative slope. The number of the value of the slope will actually be negative if we're going down. So if we were driving a car across the page, and we always go from left to right, or skiing across the page, then we would have a negative slope because this slope is going downward across the page. Okay, so that said, let's actually calculate the slope. Oh, by the way, we could have also drawn this triangle going this way. I'll just kind of dash it out. Either way is fine. We could have gone across and then down, or down and then across. That's the same exact slope. The triangle could be on top of the line or underneath the line, either way. All right, so if we're going to calculate the slope, we identify one of the points as 0.1 and one of the points as 0.2. So if this is our first point, call it x1, y1, and this is our second point, call it x2, y2. And while you're getting used to using this formula, so I'll write the formula again, m is y2 minus y1 over x2 minus x1. While you're getting used to utilizing the formula, let's go ahead and label our points, and then once you're used to doing it, then maybe you don't need to label the points, but you got to make sure that you put your points in the right spots in the formula. So the slope here is going to be 4 minus 7 divided by 8 minus 3. So we're taking our y2 minus y1 and on the top, and then on the bottom x2 minus x1. And so then we could plug that into a calculator if you wanted to, or we could just do these numbers work out kind of nicely. So -3 over 5. And again, if we wanted that as a decimal, we could write that as -0.6. We do like slopes to be as a ratio though, a rise and a run, and we'll talk about why when we get into context. But if we do, we might want to put that over 1. Either one of these would be fine for our slope. Whether you like decimals or fractions, either way is fine. So we could say that those are our slopes. And I just wanted to mention that if we had flip-flopped, if we had changed, if we had switched the way in which we had actually labeled these two ordered pairs, we would have gotten the same answer, but we have to be consistent. So if this is our first point, then both of those notations have to say 1. If this is our second point, both of those notations have to say 2. If we flip the points, we have to make sure that the subnotations are the same within each ordered pair. Okay, by the way, mentioned at the beginning that this should have been a downward slope, and you can see here clearly that this is a downward slope. And slope always has this context, right? We've gone down 3 units, and we've gone over or run 5 units. Okay, so we always have that context. All right, let's look at another example with some context. So let's look at this dosage of medicine. So let's find the slope between 2 ordered pairs from this table. Now this is the one that we use to graph, the first graph that we did. And so now let's say, what if once we've got a graph, what if we wanted to calculate the slope? And specifically between 2 ordered pairs from the table. So it says find the slope between the dosing for a 125-pound person, so 125-pound person right there, and a 190-pound person. So that would be this ordered pair. So I'm going to rewrite the ordered pairs outside the table. So this is 100, and we're looking at 125 pounds and 80 milliliters of the medicine is our first point, and our other point is 190. And I'm going to put the units on because of this particular sentence right here. It says explain this in context. So it's going to be important that we know what the units are in order to do this in context. So 190 pounds and 120 milliliters. Okay, so those are my 2 ordered pairs. I do have a graph of this simply because we did it as our first example in the graphing video, but even if I didn't have a graph, and I'm not going to show the graph, because even if I didn't have a graph, I can compute slope without a graph. And so what we do is we just say these are the 2 ordered pairs, and then we just say this is going to be my first point, so I'll call it x1, y1. This is going to be my second point, x2, y2. And my slope formula is the difference in the y's, so y2 minus y1 over x2 minus x1 over the difference in the x's. Always rise. a quick way, if you're not going to reference the formula and you're going to just try to commit it to memory, a quick way to remember it is that rise is a vertical measurement. Therefore, it comes off of the y-axis, the vertical axis. And x is a horizontal measurement, or run is a horizontal measurement, going back and forth when you're running back and forth. And that comes off of the horizontal axis, the x's. So that's the difference in the x's. Okay, so our slope here is going to be, and I'm going to drop the units until I get the numeric value of the slope. So the slope here is going to be 120 minus 80 over 190 minus 125. Okay. Now, again, we could go ahead and plug this right into the calculator. We could do the numerator and the denominator. I'm going to show two steps here. So we could go 120 minus 80, and we could get 40 in the numerator. And in the denominator, 190 minus 125, and that would be 65. We could also just have plugged this directly into the whole thing in the ratio into the calculator, and we would have gotten, it would have come out as first as the improper fraction 8 over 13. I'm sorry, not improper fraction, as the fraction 8 over 13, and we could have converted that into decimal. And so that would have come out as approximately 0.62. And I'm going to write that over 1 because we do like our slopes to be written as a ratio, a rise over run. So even if it says a decimal, we're going to put it over 1. Now, the reason we're going to do that is because we are always going to have this little piece about explaining in context. And in order to explain it in context, the slope, or anything in context that has data, we're going to need to know what the units are. And so that's why I put the units in the ordered pairs, so that when we were focused in on just the ordered pairs, we could have referenced back to the table and looked up here. On the table, the units are given at the top, and these are our x's and these are our y's. But if we wrote them right on the ordered pairs, now it becomes easy to say, okay, well, what is the numerator? The numerator here is in milliliters because those are our y's, and the denominator is in pounds. So if I'm going to write this in context, we're talking about a number of milliliters per pound. Now I'm going to go ahead and we could either use this guy. We can use any of these forms of the slope, actually. I'm just going to put the units on all of them. If we are going to talk about the context, we can use any of these three forms. So these are three equivalent forms. These are three equivalent forms, and it doesn't matter if we want to use the first one, the second one, or the third one. So I'm going to go ahead and just use the first and the last forms here. Well, actually, you know what? Our calculators would have given us the reduced forms. So let's look at this guy or this guy, the decimal form or the middle form 8 over 13. And if I'm going to write these in context, so if I'm going to write the slope in context, slope in context. So the slope in context, and we're definitely going to practice this in the homework. So the slope in context, if I'm going to write the slope in context, there are two options. So one, I'll write it in two different options. We could say this, we could say an increase, it's positive, so we have to have some sort of word about, is this an increasing slope or a decreasing slope? So it's an increase of 8 milliliters for every 13 pounds. Okay, so the dosing should increase, I should say the dosing, increase of 8 milliliters for every 13 pounds in dosing, in the dosage of the medicine. Now that's fine, we could absolutely write it that way, but we could also write it this way. We could say increase the dosage by 0.62 milliliters for every 1 pound. Okay, so that's another way to write the dosing. So increase, another way to write the slope, increase the dosage by 0.62 milliliters for every 1 pound. So either of these works. Okay, so slopes in context, either of the following. So when we talk about slopes in context, you can use either the decimal equivalent or the fraction ratio. Either one is fine, whatever makes sense. And this one I seem to prefer in terms of like the practical context of it. I actually prefer number 2. It seems to make sense to talk about every pound that a person goes up, you should increase the dosage by 0.62 milliliters. Okay, let's do one more example. Let's look at a car value. So here's a car value. Suppose you purchase a car in 2015 for $27,500, and then you track the value over the next couple of years. So in 2018 and in 2020, you have the value of the car. And we want to determine what is the slope between the years 2015 and 2020. So here's 2015 and here's 2020. So those are going to be my 2 ordered pairs. We also have this statement that we want to describe the slope in context. So let's go ahead and take a look at those 2 ordered pairs. So if this is 2015, let's call this x1, y1, and x2, y2. So I'll leave my ordered pairs in the table here because some of you will like to do it that way. But again, you have to identify which is your first, which is your second point. So if that's the way I'm going to write the slope, so remember that slope, we'll just write it again. Like I said, it's kind of like feels a little like a broken record. And I think that you will all, after doing this several times, probably have this formula committed to memory. So rise over run, and our slope for this particular example is going to be 10,700 minus 27,500 over 2020 minus 2015. So that is obviously a difference of 5 years, okay? And we do know that that is in years. That is a difference of 5 years. And then in the top, 10,700 minus 27,500, and we should get a negative value here. So this is negative 16,500. Okay, that it should be a negative value because we are decreasing in the value of the car. I'm going to put the units on it. It's a negative dollar amount. And so, I'm sorry, 800. I wrote 500, but that was actually 800. A negative $16,800 for every 5 years. Now, if I divide that by 5, I actually get negative $3,360 for every 1, because again, that comes out as a whole number. So I put it over 1 year. So if we're going to talk about this in context, we would have a sentence that says something about what's happening to the value of the car. So in context. And for this one, there was, of course, if this had come out in dollars and cents, we would have some decimals. But this one actually came out as a whole number. So in context, we would say this: the value of the car is decreasing. Okay, we have to have some language around the fact that it's going down. It's decreasing. Or you could say something like dropping. Dropping would be another word. Anything that indicates that it's going down. Dropping by, decreasing or dropping by $3,360 per year. So per every year. So when you talk about slope in context, you have to have both the actual slope with the units on it. Okay, so here's the actual slope, but you also have to have some sort of language around, is it an increasing slope or a decreasing slope? Is it going up or is it going down? Because that's telling us on the graph, is this an increasing line or a decreasing line? And in this case, this is clearly when you buy a car and you drive it off the lot, it loses value. So this context is a decreasing, a negative slope, and so we want to make sure that we capture that. Okay, so those are 3 examples of slopes. We're definitely going to do lots of slopes, get lots of practice, and so make sure that you utilize this formula, be careful about labeling your points, and then always give an answer for the slope in context.